Hello everyone, this is the project presentation by students of 3rd year Mechanical Engineering from College of Engineering, Pune. This project was done by Tanaya Bapat, Swarali Govilkar, Saibalaji Kokate and Kaushik Kunale under the guidance of Professor Abhishek Patange. The project was a part of the project-based learning for the subject analysis and synthesis of mechanisms. Through this presentation, we will take you through the process that was done in order to complete the project. Firstly, we will talk about the mechanism that was selected and the working of the mechanism. After that, we will talk about how this mechanism was incorporated in the application chosen. Next, we will explain the synthesis of the mechanism that was done both graphically and analytically. After that, we will be explaining the velocity and acceleration analysis of the mechanism. We have simulated the mechanism in SolidWorks for better visualization and understanding. After that, we fabricated the mechanism. Lastly, we will be talking about the alternative mechanisms that can also be used for the same application. The mechanism selected was crank rocker mechanism, the schematic of which can be seen. We have a fixed link, a crank, a coupler and a rocker. The crank is free to rotate 360 degree about a fixed point. The coupler connects the crank and the rocker, because of which the rocker is able to oscillate about a fixed point and the end point of the rocker traces an arc. This is the working of the mechanism. With the help of an external force, the crank is rotated through 360 degree. The path traced by the rocker is shown blue in color, and it can be seen that the rocker traces an arc. A point on the coupler is chosen and the path traced by that point is shown green in color. From this path and also by observation, it is clear that the mechanism also functions like a quick return mechanism. That is, the rocker moves quickly in the return stroke and comparatively moves slowly in the forward stroke. This property of the mechanism was made use of in the application that was designed. Moving forward to the application. In today's world, contactless processes have assumed a lot of importance. Therefore, we decided to attempt to design a contactless shopping assist. For this application, the mechanism was oriented in a different way, as is shown in the first figure. Now, because the rocker traces a particular arc, the functioning of the application is such that the application can transform objects that are kept on higher shelves in supermarkets to customers standing on the floor. The advantage of this mechanism is that a customer does not have to manually check all the items kept on the shelf, and thus the contact that the customer makes with all the objects and with different shelves is thus avoided. What happens is that the crank is rotated through an external device. A shelf is mounted on the joint between the rocker and the coupler. The mechanism picks up the object from a higher shelf, which can be seen in the second figure, and delivers the object to the customers on another level, which can be seen in the third figure. Also, because this mechanism works as a quick return mechanism, once the object is loaded on the shelf, the mechanism moves slowly and when the shelf is empty, that is when no object is loaded onto the shelf, the mechanism moves back to its original position quickly. Also, because of this particular vertical orientation of the mechanism, a lot of space is saved.
Now we will look into the synthesis of the mechanism. Following assumptions were made which also give an idea of the complete process. Initially, the chosen mechanism was modeled and simulated in SolidWorks for various combinations of lengths of links, and one set was selected as reference for graphical analysis. The graphical analysis is done by body guidance method. Thus, 3 positions of coupler were to be decided. The extreme positions of coupler and length of the coupler were acquired from the reference model. Position 2 was chosen by selecting B2 to be approximately halfway through between B1 and B3, and inclination was finalized through iterations for a range of angles ranging from 20 degrees to 30 degrees. The results of graphical analysis were again modeled and simulated for verification. Further, the initial values for angles in Freudenstein's analysis were taken from the simulation. Both graphical and analytical results were verified. Working model of the mechanism was fabricated for the results obtained through analytical synthesis. The final model used in the application is a scaled-up model to satisfy the objective of the application. The model has been scaled up by 4. The angular velocity considered in velocity and acceleration analysis was chosen such that delivery was quick but not too fast to damage the contents of the same. Graphical analysis. The graph shows the graphical synthesis of the mechanism. The scale of the graph is 1:2. A1B1, A2B2 and A3B3 are the 3 different positions of the coupler. OA and OB are circumcenters of triangles A1, A2, A3 and B1, B2, B3 respectively, which have been plotted using geometrical constructions. The results obtained for the lengths of the links from graphical analysis are the length of the input crank A, that is OA-A2, is equal to 54 mm. The length of the coupler as taken from the reference model is 210 mm. The length of the rocker arm C, that is B2OB, is equal to 154 mm, and the length of the fixed link D, that is AOB, is 133 mm.
In the analytical method, we verify the results obtained from the graphical ones by using the Freudenstein's equation. Following is a derivation of the Freudenstein's equation, wherein we assume a auxiliary 4-bar chain and derive the Freudenstein's equation. So as shown, the lengths of the links are A, B, C and D. So for equilibrium, the summation of vectors in x direction is 0, and so is the summation of vectors in y direction equal to 0. On solving the equation, we get the final Freudenstein's equation as cos theta minus phi is equal to k1 cos phi minus k2 cos theta plus k3, where k1 stands for d by a, k2 is d by c, and k3 is a square plus c square plus d square minus b square upon 2ac. Applications of Freudenstein's equation to our problem. So our requirement was that the mechanism should sweep 80 degrees for proper pickup and drop. So as shown, the initial sketch is shown in the figure. From graphical analysis, we take 3 values of theta and phi, for which we apply the Freudenstein's equation and verify the results. So the 3 pairs of theta and phi are 45 degrees and 34 degrees, 91 degrees and 60 degrees, 237 degrees and 110 degrees. Upon using the Freudenstein's equation, we get 3 equations as shown by A, B and C. And on further solving them using Gaussian elimination, we get the value of K1 as 2.270, K2 as 0.8592 and K3 as minus 0.2931. Using the values of K1, K2 and K3, we find the values of A, B, C and D links. which come out to be A is 54 mm, B is 206.91 mm, C is 142.667 mm, and D is 122.58 mm, which is very close enough to the graphical results obtained. Hence, we use these values of lengths for our model making.
The velocity and acceleration analysis is done using the relative velocity method. Here you can see the configuration diagram, which is drawn at theta is equal to 45 degrees and phi is equal to 34.5 degrees. The link lengths used in the diagram are mentioned in the table below. The angular velocity of the link AB is assumed to be 15 rpm, which is assumed so to suit the requirement of the application. Here you can see the velocity diagram and the calculations done to calculate the respective velocities of the link. The result of the velocities calculated is shown in the table. With the help of the velocities and angular velocities calculated, the acceleration diagram is drawn, which you can see over here. And here you can see the calculations used to calculate the respective acceleration of the links. The result obtained by the calculations is shown in the table.
This is the simulation for the application of the mechanism. The shelf can be made according to the requirement of the user. We have shown a representation for the shelf and an object is kept in it. This is where the object will be picked up, and then the crank is rotated. At this point, the object is delivered.
This is the fabrication of the crank and rocker mechanism. The red link is the input crank, the yellow link is the coupler, the green link is the fixed link, and the blue link is the rocker. The lengths of the links are the ones obtained by Freudenstein's analysis. Now here, the sum of the smallest link, that is the input crank, and the largest link, that is the coupler, is less than the sum of the fixed link and the rocker. Thus, the mechanism satisfies Grashoff's law, that is, S plus L is less than P plus Q. As a consequence of which, there is at least one link, the smallest link, input crank in this case, has the freedom to complete one full rotation. The functioning of the mechanism is such that when the crank is rotated, the joint between the coupler and the rocker traces an arc back and forth, that is this point. Now if you observe carefully, the extreme positions of the arc are obtained when the input crank and the coupler are collinear with each other. 1 and 2. In this case, the coupler and the input crank overlap each other. That is, the input crank makes an angle of around minus 120 degrees with the fixed link, that is the x-axis in this case. The other opposition is obtained when the input crank makes an angle of about 20 degrees with the horizontal. Therefore, the forward stroke is from 240 degrees to 20 degrees, while the backward stroke is from 20 degrees to minus 120 degrees. That is, the input crank travels through 220 degrees during the forward stroke and only 140 degrees during the backward stroke. Thus, the backward stroke is faster and hence the quick return mechanism.
Now we will discuss some alternative mechanisms which can provide us the same function. First is Whitworth quick return mechanism. The point P goes from P2 to P1 in the backward stroke and point P1 to P2 in the forward stroke. And when it goes from P2 to P1 in the backward stroke, it goes much faster as compared to when it goes from P1 to P2 in the forward stroke. And the second mechanism is the crank and slotted lever quick return mechanism. In this, the forward stroke is performed when the crank goes from B1 to B2, and the return stroke is performed when the crank goes from B2 to B1. As we can see, the angle covered in the forward stroke is beta and in the return stroke is alpha. As alpha is lesser than beta, the return stroke is performed much quicker than the forward stroke.